Hello, welcome to Digital Gravity Lab. I'm Matthew Richler, and this is my first programming assignment as a PhD student in the Computational Sciences and Engineering program at Harrisburg University. So I'm going to jump right in here. So this gave me a lot of trouble originally setting up the environment, but now I have figured out the steps, and particularly around installing the environment with Anaconda Navigator, the CUDA toolkit, Microsoft Visual Studio 2022, and then the once you have it there, the various environment programs and libraries that need to be set up in order to get it to run effectively. And in that whole process, I did various versions of system scans in order to see what my system was running. And you can see here the Microsoft Visual Studio and Insight systems, just the path wouldn't run, so had to plug that in directly. And this here looks at the CUDA version and things like that, make sure it's set up with the final directory here at the bottom. Most of the time, at least two of these were coming blank. So yeah, it took me many hours to get everything functioning correctly in an environment that was, I could reset if I needed, and or I'm basically planning for every programming assignment to do a new environment to start from scratch. So for these three assignments, for map, reduce, stencil, we're looking at serial baseline, use NumPy, Python, need to have a native GPU kernel, optimized GPU version, and then this was just the first example there of a map, and here you can see the map element-wise transformation. So for example, this linear equation where you're, or nonlinear, where you're setting up the whole thing with x and y and adding it together, mapping it. So the first thing that I did here was this, because I couldn't get the other CUDA libraries to work, this MVCC for Jupyter was actually the first thing I got working, but basically that directly runs C here using this CUDA and this whole library here. I was able to get quite a bit of this running, all the way. The profiling I honestly couldn't get running on my computer, so I still have to learn how it all works. But the first threads, this hello from the block thread was the first thing that I was able to actually get running from parallel in the GPU. So that said, just moving along here, this other version of using CUDA JIT, right? It's that CUDA Nimba, which is Python. Getting that to work, and then testing out in various threads per blocks, which then kind of auto figured out how many blocks it was, and you can see very slow speeds here, simply because of all the overhead in order to transfer over. So as we go up to 1 million variables, it starts getting a little bit more reasonable in the speed, and of course anything over 1024 crashes and errors out if you try to run it, and then just trying different number of blocks and sizes. So then this one was 10 million. You can see the speed continued to increase as far as total bandwidth, speed, and then, but I mean there was a certain level where it averaged out, and then this is the earlier version. This is the first version that ran a lot simpler, noting that in order to figure out how this works, get things, understand it, I am partway through this course, Fundamentals of Accelerated Computing with CUDA Python. Highly recommend it. It's only $80, but it's worth more than the textbook for sure, and has a whole environment and everything to run it in. So very efficient in learning. Really like that so far. But that's been able to help quite a bit. And noting, of course, as every time you run it, especially in these smaller ones, there's a lot of variability in the speeds. So if you were to just rerun some of these, you can see every time it's reran, the kernel time is quite a bit different, which, as you kind of saw there, the first time was slower than after that. And then it kind of, it's already warmed up, and it works a lot better. So there you go, 4 times faster than the last time I ran it. Similar end-to-end kernel time though. Right, same warm up. Once it's already warmed up, you can see much faster times than it had before. Then there's also, to compare it, the CPU functions here. It's CPU for a smaller amount is actually almost always faster. And we did do some tests here for performance of math functions with Pythagorean theorem, right? And tests we're using TimeIt. TimeIt does only work with CPUs, but yeah. And testing that, the optimized math version versus the Python function versus the creation of a JIT version here, the optimized version is much faster, but even the parallelized version is still much faster than the standard Python function, not optimized version. So and then we just did a CPU versus CPU time. You can see over, how many milliseconds took over 1,000 runs, and with an average 0.16, right, going back up to still, it's a lot slower than the average for the CPU, but not by much. Not by, milliseconds. So I like 1,000 times in this case because it's only 1,000 runs. So there's a lot of overhead. But oh well. That's kind of standard. There's a lot of overhead, and the GPUs are much slower. They're only really useful if you have large parallelized processes. So knowing when to use CPU and GPU is a big thing. Going into reduce, right? So reduce, basically the primary thing is taking a sum of the elements, or like this array, and turning it into the vector into a sum of elements or product of elements or whatever it is, which normally then means the actual value. So taking these two arrays in this case, and just adding them together, you get the value here. And then there's various tree-based reduction ways to divide the threads as you go through. If there's, right, instead of just going straight across like this one did, but taking those arrays and turning them into a single value, the having threads is every time it does that calculation, it uses half as many threads. And so then, but then using that tree-based reduction here versus the warp shuffles, right? 16, 8, 4, 1. Going down, and then dot products, right? So just multiplying across various arrays, or like these two arrays, just giving the product in the new one. Similar T-based reduction of dot product, splitting in half every time, and then warp reduction, right, where you just taking half as many threads to multiply it across. And then, so that's this whole process here, and this taking these values, multiplying down, getting 50, and then taking this whole thing and trying to optimize it, looking at threads per blocks, blocks per grid, the setting 80, 160, 320 as just like forced ones, but then optimize, you can see it's many blocks per grid, which is again relative to how many threads per block is used. So it's just optimizing that, and you can see it is a little bit faster by doing it that way. And looking at kernel versus total, versus the total output, you can see the throughput, but everything ran. Though it gives errors, too little use. Going here to Stencil, which was the last thing we did here. Here's kind of a little explanation here, but primarily it's used for image processing, or in physics for heat diffusion or machine learning. But it's basically taking an array, so like in this case, applying some kind of filter, which in this case just looks at the edges and cuts off the edges, essentially in this case. But there's many uses of that, but with stenciling, all the photo apps that apply filters, it's a big thing that they do. So one of the first runs that we did in CUDA, right, put in this whole array, and it just chopped off the end, put zeros at the end, and looking at input, native, shared memory, right, so the both of them worked. But looking at the performance, native is pretty much always faster. I think every time I run it, it does give a slightly different graph, but I guess that partly depends on whether I'm using the computer at the same time or something like that. And then running down here, doing other optimization attempts. Again, looking at the various quantities, looking at the grid size, the threads per block, and just seeing what could optimize it. Native is always better. The registered tile did get better in a few cases, and so then we used the tuner as well. That was a lot more cleaner. But then we tried setting a threads per block 128 versus the tune, see kind of what the tuner would do, and there, but native still always faster. We didn't go too much larger. I mean, I guess maybe if we used much bigger, but I mean, you can see here we're already 100 million from blocks, but there we go. This is my project here, first programming assignment, and I thought it went really well after I figured everything out. ChatGPT Pro and a little bit of Perplexity was normally helpful, but it wasn't actually helpful until I knew enough in order to say which programs to use, and things. So the first one I got running, this NVCC for Jupyter, once I knew that kind of worked, I plugged that in, told it to use it, it worked, but without it, it didn't. So and then again, doing the course, NVIDIA, I was able to figure out whether I was getting good data out from the various GPUs in order to build this. So thank you very much, and until next time.